Okay, if you didn't see the email, homework 2 is now on Sakai. If you haven't turned in homework 1 yet, please try to turn it in as quickly as possible so that we can get it graded and handed back. And, yeah. Today, we're doing a little more of the theoretical stuff. Again, I apologize for inflicting this on you, but this is one of the most important results in statistics, so I feel like I kind of have to explain what's going on here. Hopefully after today, there won't be much in the way of theory for the rest of this course. So, recall that, and it looks like we have another nice little issues converting between PowerPoint and Keynote, that the bars disappeared on all my x's. That's supposed to say the difference between x and x bar, where x bar denotes the sample mean, just the mean of what's in the data set. And yeah, if you look at the PowerPoint or PDF files on Sakai, it's correct. I apologize for that. As I say, I have to record the lectures and Keynote, so I don't have much choice here. We make a distinction between an individual data point x and a population mean x bar. The idea is that x would be the income of one particular person, or one particular person's SAT score, the weight of one particular mouse in your lab, whatever the case may be. Whereas the sample mean x bar would be like, say, you select 100 people, ask them what their income is, take the average, select 100 students, find the SAT scores for each one, take the average of that, or take the average weight of an entire litter of mice in your lab, or whatever the case may be. And to give an example, and basically the distribution of the data for an individual observation can be quite different from the distribution of the data of a sample mean. Now I'll illustrate that with this data set in R that consists of the height of 85 Loblolly pine trees. And basically we want to see what inferences can we make about the distribution of the original data and the distribution of the sample mean. So the first thing we did here is plot a histogram of the original data X. These trees came from forests in several different locations, so there's quite a bit of variability in the heights of these trees, and it's definitely not anywhere close to being normally distributed. We've got a bunch of really short ones, a bunch of tall ones over there. We certainly do not see the standard bell-shaped pattern with the heights of most of the trees close to the mean, and with fewer and fewer observations away from the mean. Forget, there's about 96 observations in this data set. I think I said it on the previous slide. One way or another, this data set is built into R. It's called Loblolly, I believe, if you ever want to play around with it. But so, as I said, the X is definitely non-normal. The shortest tree in this data set is 3.46 meters. The tallest tree is 64.1 meters. The mean height is about 32 meters with a standard deviation of around 20 meters. Quite a bit of dispersion in this data. Now, let's talk about, it's supposed to say the distribution of x bar. We know that the distribution of x is highly non-normal. Let's say we want to calculate the distribution of the sample mean. I guess there's 85 observations in this data set. So I won't show you the R code for this because it doesn't really matter, but I used R to just randomly generate samples of size 4 from this data set and took the mean of each sample of size 4. So basically, it was just a random sample each time. Say we numbered the trees from 1 to 85. The first time I may have selected tree 1, tree 17, tree 36, tree 68. Then the next time I may have selected tree 5, tree 12, tree 24, tree 57 sort of thing. Each time I just took a random sample of size 4 from these 85 trees, and each of these random samples I took the mean. So I have 85 means now rather than 85 individual observations. So let's plot the histogram of these 85 means and see what they look like. And it's kind of interesting. We'll recall the original data set was extremely non-normal, but you look at the histogram of X bar, like I say once again, it's supposed to be X bar, not X, and it's already starting to look kind of bell-shaped. I mean, there's a couple abnormalities here, but it's definitely looking much more normally distributed than the original data was. And so let's take the summary statistics of the original data versus the summary statistics of this set of sample means of size 4. And as you can see here, the sample mean of the original data and the sample mean of this set of 85 means is a little bit confusing. I'm taking means of means here. I got 85 sample means, then I took the mean of those 85 means. It's almost exactly the same as the mean of the original data, but notice the variance of the new data of this set of sample means is reduced. For the range went from 3.46 to 64.10 with standard deviation of about 21. Now in this case, the minimum value is 8.67, the max is 60.37, and the standard deviation is about halved. It's down to about 11 now. I mean, this makes intuitive sense that if we were just sampling from the original population, we would have to get a tree of height 64, we just have to choose that particular tree. If on the other hand we go from a sample of size 4, the only way to get a sample mean of 64 is if we drew that same tree 4 times in a row, which is very unlikely to happen. In fact, it's impossible if we're sampling without replacement, which is what I did here if I remember correctly. So it makes intuitive sense that when you take the average of things, you're most likely going to get something closer to the population mean and less likely to observe an extreme value. So once again, this is supposed to say a comparison of X and X bar. The mean of X is nearly identical to the mean of X bar. They're both around 32. But the range of the sample means is smaller, and the standard deviation is about half of what the standard deviation was for the original data. And if we draw the histogram of the distribution of sample means, it's much more bell-shaped than the histogram of the original data. The original data wasn't even close to being normally distributed. Even with the sample size 4, it looks like we're starting to see some evidence of a normal distribution going on here. So then I repeated this process, taking samples of size 10 rather than samples of size 4. This is the histogram again. It's looking quite bell-shaped at this point, a little bit irregular, but you would call this approximately normally distributed just about any day. And we compute the summary statistics again. We see the same general trend. Once again, the mean of the means is almost exactly the same as the mean of the original data. Now the range is considerably smaller. We don't see anything smaller than 16 or larger than 47. And the standard deviation has gone from about 20 to about 7 in this case. And just to show the general trend, I did this again with a sample, taking sample means of size 30. And for some reason, actually, this doesn't look as bell-shaped, maybe just because there's too many bars on the histogram, but it's definitely still a strong bell-shaped trend here. And we look at the distribution of x bar in this case, we end up with an even narrower range going from 22.54 to 41.44. Again, the means are virtually identical. The standard deviation in this case is now down to about 3.5. We see the general trend here that as the sample size of the things that we're taking the mean of increases, the mean of the means always remains about 32, about the same as the mean of the original data, but the standard deviation steadily decreases each time we increase the sample size. And here we show the effect of the sample size n on the distribution of x bar. As the sample size increases, the mean of x bar, the mean of the sample means, doesn't change, but the dispersion of x bar decreases steadily. We can see the trend here that the sample means stay about the same regardless of the sample size. The minimum is getting steadily larger, the maximum is getting steadily smaller, standard deviation is steadily increases. We also saw from plotting the histograms that the distribution of the sample mean x bar becomes steadily more bell-shaped as the sample size increases. And if you remember from Monday's lecture, we showed using these properties of expected values and variances that losing all those bars in the conversion to keynote really messed this up, didn't it? It's supposed to say the expected value of x bar equals the expected value of x. The variance of x bar equals the variance of x divided by n. So in other words, the standard deviation of the sample mean should be the standard deviation of the original data divided by the square root of the sample size. And as you can see from the table down here, that's consistent with what we observe in this data, that SD underscore should be x bar gives the standard deviation that I calculated when I did this simple numerical experiment, and this SD of x divided by the square root of n gives what the standard deviation is predicted to be under the theoretical result up here. And we can see the theoretical standard deviation is almost identical to the actual observed standard deviation. So this pattern that the standard deviation decreases with inversely proportionally to the square root of the sample size seems to hold true in this case. So it turns out this pattern here, where if you take a sample mean as n is the size of the sample mean increases, you get something that's closer and closer to the population mean, something that looks more and more normally distributed, is not a coincidence. This is an example of what's called the central limit theorem, which is one of the probably the single most important result in statistics, a result which virtually all of the commonly used statistical tests depend on, is the result on this slide that says you draw a sample of n independent observations from any population with mean mu and standard deviation sigma. Then, as the sample size increases, the sampling distribution of the sample mean x bar becomes approximately normal with mean mu and standard deviation sigma divided by the square root of n. So the implication here is no matter how messed up and ugly and horrendous your original data is, if you sample from that population, take the mean, it's going to be normally distributed. It's really kind of a remarkable result when you think about it. And note in passing down here that if x bar is distributed normal with mean mu and variance sigma squared over n, then if you take the square root of n times x minus mu divided by sigma, you get something that's approximately normal with mean 0 and standard deviation 1. That result isn't as important now as it used to be when we still had to use these normal tables, but it's still useful on occasion, as I'll show you in a minute. And just for emphasis, the main reason that the central limit theorem is so remarkable is you can draw a sample of n independent observations from any population, and as n becomes large, the sampling distribution will become normally distributed. Turns out you can find cases where this doesn't work, but you're not going to see them in real life unless you're going out of your way to find a horrible data set to try to break this. I don't think I've ever seen a real world data set where this breaks down for sufficiently large n. And I'll show through the course of the rest of today and the next week or two why this result is so useful. This central limit theorem means that even if the population you're drawing from has a really bizarre, messed up distribution, you can still make inferences about the sample mean and calculate confidence intervals and so forth. So, a good question about this is, how large does your data set have to be for the central limit theorem to work? It turns out not that large, which is really convenient. That if your data set is reasonably well behaved, the central limit theorem will probably give you reasonably normal results for n equals 10 or even n equals 5. I mean, we saw this with the Loblolly pine data. I just took a sample with n equals 4 and a data set that was not all that normally distributed. Its histogram was already reasonably bell-shaped. In that case, you may get away with applying the central limit theorem with n equals 4 without getting into trouble. Now, it's usually when you get into trouble trying to apply the central limit theorem, it's usually skewness and outliers that will get you into trouble. If your data set's skewed or has bad outliers, you may need something like n equals 20 or n equals 30. If you have like the most ridiculously skewed data on the entire planet with tons of garbage observations that weren't removed, it's basically everything that possibly could go wrong does go wrong, then you need like n equals 70 or 80. So the bottom line is, even for relatively small samples, the central limit theorem holds. And I mean, in practice, very rarely when people write papers do they even bother to check to make sure the central limit theorem is holding when they apply their data. They just run the test, and in 95 to 99% of situations, it's fine. Just to give a numerical example of this phenomena, this is simulated data from a really skewed distribution. As you can see, most of the data is concentrated around 0, but a very small proportion of the data is much larger, and you can't have any observations less than 0. You just draw 2 observations from this particular data set, calculate the mean. It's already starting to look somewhat bell-shaped. By the time you get to 10, it's pretty nicely bell-shaped. By 25, it's almost perfectly bell-shaped. So even when you have relatively bad data like you see in this slide, for a sample of size 25, you're still in pretty good shape. That said, that does not mean that you should just run out and apply the central limit theorem willy-nilly to any data set that you collect. The one place where the central limit theorem is most likely to blow up is the n observations that you draw have to be independent. If they're not independent, you're just about dead in the water. I mean, there's some things that you can do, but they're complicated and definitely not something I'm going to discuss in this class. So, if the independence assumptions are not satisfied, do not attempt to use the central limit theorem, do not attempt to draw inferences about the mean, because you will get incorrect results. The most common ways that you will get into trouble with this is if you have like time-ordered data that, say, you run some type of experiment and you collect data every 2 hours or so. It does not work to simply take the mean of your 10 time-ordered observations and try to make inferences based on that mean, because the observations are not independent. Another case, if you have like spatially related data, this is most common in agricultural experiments. You have one plant in a plot here and another plant in a plot right next to it. Those are probably not independent, so you can't just average across that. Oh, when the central limit theorem blows up in your face, it's almost always an independence issue, even when your data is really badly behaved. As long as the observations are independent, you're usually fine, but if they're not, you're in trouble. And for those of you who have a good memory, I will give you a heads up on one homework assignment that will be coming out in a week or two that has given people trouble in the past, where I asked them to make inferences about a sample mean of a particular data set where the observations are clearly not independent, and you end up with some really ridiculous results, and I asked you to explain why. So keep that in mind when you do upcoming homework assignments. Oh, little terminology here. As noted earlier, for n sufficiently large, the sample mean x bar will be approximately normally distributed with mean mu and standard deviation sigma divided by the square root of n. This quantity sigma divided by the square root of n, or more commonly s, the sample standard deviation divided by the square root of n, is known as the standard error. And the standard error is important for reasons that you'll see very soon, that if you want to calculate confidence intervals for the mean, the width of the confidence interval will be proportional to the standard error. So, just to give an example of how one might use the central limit theorem in real life, this will be the same example for Monday. Say you have a hospital, and the newborns have a mean of about 112 ounces and a standard deviation of about 20.6 ounces. And we know birth weights are not normally distributed. They tend to be really heavily left skewed because some babies are born prematurely and are much smaller than the remaining babies. So let's say that we want to compute the probability that a random sample of 10 babies has an average weight of greater than 126 ounces. Well, the first step here is to compute the standard error. In this case, we know the standard deviation is 20.6. To get the standard error, we just take the standard deviation divided by the square root of the sample size. In this case, it's about 6.51. So the sample mean should be approximately normally distributed with mean 112 and standard deviation 6.51. Oh, just to visualize the section of the normal curve that we're trying to approximate, I drew the picture here. When you work the homework, if you're having trouble wrapping your brain around this, sometimes it helps to sketch a little graph like this to visualize what area of the normal curve you're trying to figure out. In this case, we want to find the probability that the 10 babies have a mean birth weight of greater than 126. So we want this region of the normal curve. The command in R to get this is pnorm, as we discussed on Monday, that pnorm can give us the area to the left of the red hand side, and since the area under the entire curve is 1, to get the red area we can take this area using pnorm and then subtract it from 1. So in other words, if we go 1 minus pnorm, 126, comma, the sample mean, which is 112 in this case, and the standard error, which would be 20.6 divided by the square root of 10. See, there's a probability of about 0.016 that a set of 10 babies has a mean birth weight of 10 or higher, or 126 or higher. And just a quick note on our syntax, this command square root sqrt gives the square root of x. So square root of 4 is 2, square root of 9 is 3, so on. Hopefully that's easy enough. So let's say we want to do a slightly more complicated example. Let's say that we want to find the probability that a set of 10 babies has an average birth weight between 112 ounces and 126 ounces. In this case, we want to find the area of the red region in this graph. The simplest way to do that is to take the area below 126, the left of that, and then subtract off the area to the left of 112. So it would take basically p norm 126 minus p norm of 112. So there's the commands in R, p norm 126 with the appropriate mean and standard deviation minus p norm 112 with the appropriate mean and standard deviation. We get a probability of about 0.484 that a sample of 10 babies will have a birth weight in that range. And now let's do an example that is more common in the scientific world if you're trying to write a paper or whatever. Let's say that you take a sample of 10 babies from this population and you want to find the 95% confidence interval. That is an interval such that there's a 95% probability that it contains the true population mean. So, as I said on Monday, the easiest way to do that is to find the 2.5% and 97.5% quantiles of the distribution. So in this case, you can use the qnorm command as we discussed on Monday. Qnorm 0.025 with the appropriate mean and standard deviation. Qnorm 0.975 with the appropriate mean and standard deviation. That implies that 95% of the time, if you take a sample of size 10 and take a mean birth weight of 10 babies, 95% of the time the mean should be in this interval from about 99 to 125. And this is an extremely handy result in the scientific world. It means that if you're doing an experiment, say on rats, you collect some measures from 10 rats, you can take the mean across these 10 rats and then say, a 95% confidence interval for this mean is whatever the numbers are. Most journals will insist that you report something like this in order to get your paper published, so useful to know how to do. And one little warning about the method that I just outlined is this approach only works if you know the population standard deviation sigma. In practice, this is a completely idiotic assumption because basically the approach I just outlined only works if you know the standard deviation, you don't know the mean. Well, number one, how would you, given that you need the mean to calculate the standard deviation, I don't know how that would ever happen. And number two, it's like, if you know the standard deviation, why are you bothering to do this experiment in the first place? So this is kind of an artificial example, but luckily there's still a way to calculate confidence intervals for the mean, even when the standard deviation's unknown. I'll discuss that, I think, on Friday or maybe next week. But for the time being, this is just to illustrate the principle of how this works. that using the central limit theorem, you can calculate confidence intervals for the mean, even if the distribution of the original data is really ugly. So, now I'll briefly illustrate some ways that you can get into trouble trying to apply the central limit theorem. Let's say that you wanted to find the probability that a single baby has a birth weight of 126 or greater. Might be tempted to just use the R command, say, okay, in this case we have a sample of size 1, the mean is still going to be 112, the standard deviation is going to be 20.6 divided by the square root of 1. We'll just take 1 minus p norm of that to get the probability. Well, that doesn't work. Recall that the population is not normally distributed. The distribution of the birth weights of these babies is very highly non-normal. It's badly skewed to the left because of low birth weight babies. So the fact that X bar may be normally distributed for a sample size 10 does not imply that the original data is normally distributed, so you can't make inferences about a single observation. So you just don't want to apply the central limit theorem to individual observations. And even if you're averaging a small number of observations, it's dangerous. You'll get away with it if your data is sufficiently well behaved, but if your data is ugly, then you'll get invalid results. And another way that you can get into trouble with the central limit theorem is, well, I'll save the punchline for a few more minutes. Recall an example from, I think it was last week, of the French stock market index with where like the average closing value over 10 years was 2,228, and the standard deviation was about 580. So, if one were to mindlessly apply the central limit theorem here, you might think that let's just take 100 consecutive days somewhere in that time interval and take the mean. That should have a mean of 2,228 and a standard deviation of 580 divided by a square root of 100, in other words 58, right? Well, let's see if that actually happens. So, this data set's built into R for the sake of this example. I randomly selected a 100-day interval from this time period and found that the mean value of the index during this 100-day interval was 2,904. So let's try to use the central limit theorem to say what's the probability of selecting a sample of size 100 with a mean of 2,904 under the central limit theorem. So I do that in R using p norm. What's the probability of observing a mean of 2,904 or greater given that the population mean is 2,228 and the standard deviation is 58? And as you can see, it's 0. It's not actually 0, but it's like ridiculously tiny. I mean, I would win the lottery 3 times in a row before I would observe a mean that large under the central limit theorem. So what went wrong here? Well, as I said before, the issue is the observations are not independent. If your independent assumption is violated, the central limit theorem is completely invalid. I managed to choose a 100-day interval where the stock market was doing particularly well, and it wasn't representative of the mean of the overall population. the intuition here is that if observations are correlated, then each observation provides much less information about the true mean. The stock market, very rarely will the value change by more than 1 or 2% from day to day. So if I have the stock prices for 10 days in a row that are highly correlated with one another, that's much less information than if I had 10 independent observations. So if you have correlated data, the true standard error is much larger than simply sigma divided by the square root of n. Like I said, if you have correlated data like this, there's ways that you can correct for it. And I mean, if you have any data like that in your own lab work or whatever, you're welcome to talk to me and I'll try to help you with it. But it's complicated and ugly stuff and not something that I'm going to ask you to know in this class. So, things to remember for today is that a sample mean x bar has a different distribution from that of an individual observation x, and if observations are independent and the sample size is sufficiently large, then the sample mean x bar will have approximately a normal distribution. And if the sample mean has a normal distribution, then we can do useful things like calculate confidence intervals for a mean, or test hypotheses that your mean is equal to a certain value or whatever, all of which I will describe in more detail over the next week or two. In order to do this, you have to make sure that your sample is sufficiently large and that your observations are truly independent. If they're not, then you'll get into trouble. Any questions about anything today? Should ask more questions. We keep getting out way early. Well, for some reason nobody ever complains when that happens, so I guess it's okay. Anyway, see you on Friday.